So at the level of the presynaptic neuron, you see that we have a number of different features that are all related to the containing and transmission of chemicals. Now, what's going on here at the edge of the dendrite? This is somewhere that we see the release of neurotransmitters, the blue circles, into a space that we call the synaptic cleft. Now, the synaptic cleft is a fluid-filled space within which the neurotransmitters will freely float before they make contact with the postsynaptic neuron. So here we've got the cell wall of the postsynaptic neuron. You can see we've also got some mitochondria in this cell. That's more protein. We've also got a layer here where there are small gates that are either open or closed, and these gates are allowing the transmission of the neurotransmitter from the presynaptic neuron to the postsynaptic neuron in a controlled way. So again, it's another hydraulic metaphor where the water that flows, or the fluid that flows from one neuron to another, is controlled via a lock and a gate, where the amount of material that is transmitted is regulated. So back to the presynaptic neuron, we can see that the first point before the neurotransmitter is released is called a docking station, and the vesicle lands at the edge of the dendrite wall and is at this point closed. But due to some magical physics that I'll describe in a minute, sometimes these neurotransmitter vesicles will open and release the neurotransmitter into the synaptic cleft, and that's what's going on here. The technical term for the opening of these vesicles is a fused vesicle, as it springs open and releases the neurotransmitter. Now, on the other side, the presynaptic neuron is feeding neurotransmitter to the postsynaptic neuron via a principle of electrical charge. The substances that are in the synaptic cleft will flow into and out of the postsynaptic neuron depending upon whether or not the electrical charge of the synaptic cleft is positive or negative. And when we see the transmission of substances from one neuron to another, what we're seeing is the rebalancing of positive to negative charge within the synaptic cleft that enables these gates to either open or to close. Here we've got some examples of open gates, and what's important to understand is if you look very closely into the synaptic cleft, not only is there neurotransmitters, but there are these tiny little black dots which are referred to as sodium ions. And sodium is simply a chemical that is salt and is in fact positively charged, Na+. Ion refers to the positively charged sodium atom, which is located within the synaptic cleft, but also you can see within the postsynaptic neuron. Here are some little sodium ions floating about after the gate. Now, why do we have these little sodium ions floating about? Well, the reason is that the opening and closing, the mechanics of the opening and closing of these gates depends upon the relative balance of sodium in the synaptic cleft and sodium within the postsynaptic neuron. And if there's an imbalance between each of these sodium ions within the synaptic cleft and the postsynaptic neuron, then we'll see either an opening or a closing of these particular gates. At this stage, I want to use a metaphor that I think you'll find useful, because I'm going to talk again about a different chemical called potassium. And if you think about this outside surface in the postsynaptic neuron as being like a banana, and I'll explain why in a moment. So imagine that this is a banana. Think about the outside of the banana, that's the area along here, as being salty, a salty banana. And I'll explain why that's useful in the next slide.